Hello, my name is Jonathan Takeshita, and I'm presenting on the paper Algorithmic Acceleration of BFV-like Somewhat Homomorphic Encryption for Compute-Enabled RAM at the Selected Areas in Cryptography 2020 conference. My co-authors are Dayane Reis, Dr. Michael Niemier, Dr. Sharon Hu, and Dr. Taeho Jung, and we are with the Department of Computer Science and Engineering at the University of Notre Dame. Homomorphic encryption schemes allow computations over encrypted data. The most powerful homomorphic encryption schemes are fully homomorphic encryption schemes, which allow arbitrary computation on encrypted data. In practice, somewhat homomorphic encryption schemes, which are limited in their multiplicative depth, are often utilized. Modern homomorphic encryption schemes are lattice-based and draw their difficulty from the ring learning with errors problem. The computational overhead of fully homomorphic encryption and somewhat homomorphic encryption is high, because the operands are polynomials with thousands of coefficients. Each of those coefficients will be hundreds of bits wide. Ordinary CPUs are not well suited to computations on these large operands. Many research efforts have been made to accelerate homomorphic encryption. Some are purely algorithmic, and some are hardware-based. Of the hardware-based ones, platforms such as FPGAs, GPUs, ASICs, and compute-enabled RAM have been utilized before. The algorithmic efforts include use of the number theoretic transform and full RNS variants. CPUs, FPGAs, and GPUs all have the critical weakness of a separation of memory and processing elements, which incurs high overhead from data transfer. This is a serious problem for homomorphic encryption because of the amount and size of data in HE homomorphic encryption operands. Most conventional hardware is also restricted with hard limits on word size. For example, 27 bits in a word for FPGAs or 64 bits in a word for CPUs. Hardware such as compute-enabled RAM, CRAM, can bypass these limitations. Our prior work has shown the efficacy of applying CRAM to homomorphic encryption. Even without any algorithmic optimizations such as the RNS variants or the NTT, CRAM was able to improve on state-of-the-art FPGA implementations of BFV. CRAM does have some limitations in implementation, which we'll discuss later. In this work, we improve upon the prior implementation of BFV in CRAM by applying algorithmic optimizations. Data transfer between memory and processing elements is a large bottleneck for many applications, including homomorphic encryption. Compute-enabled RAM, often referred to as CRAM, is a hardware paradigm that eliminates the separation that is inherent in other computing models. So some of the strengths of CRAM include its integration of memory and computation that give it such speed, and its lack of bounds for a hard word size. CRAM technology is still developing, and some operations are not yet supported, such as multiplication and division as primitive operations, or floating point capabilities. Homomorphic encryption schemes are formalized as a set of algorithms. The first algorithm is for key generation, and it generates a public-private key pair along with any other parameters needed. The second is encryption, which simply takes a plaintext message and the public key and returns an encrypted ciphertext. The third is decryption, which takes a ciphertext and the private key and returns the decrypted message. And then the fourth evaluation is to take in a list of ciphertexts and perform some homomorphic computation on them. And evaluation is usually functions for addition and multiplication. This slide shows the formula of decryption in the BFV crypto scheme. So to decrypt with a plaintext modulus t, you would compute the formula shown here. This formula can be easily computed in CRAM when q is a power of 2. However, if you use other moduli, as needed for the full RNS variant, then this becomes more difficult because CRAM has trouble with general division. The formulas for homomorphic multiplication in BFV are similar. You'll notice that they share the same division with rounding primitive that decryption does in BFV. So similarly, we have the result that CRAM can compute this easily when q is a power of 2, but it may not be achievable quite as easily when q is not a power of 2. Now let's talk about some algorithmic optimizations. The number theoretic transform, which is a variant of the discrete Fourier transform, can be applied to reduce the overhead of polynomial multiplication from O of n squared to O of n log n. To enable the NDT, q should have a primitive root modulo 2n easily findable. This is normally satisfied by requiring that q is equivalent to 1 modulo 2n. Another optimization we can use is the residue number system. So if we let Q be the product of k coprime numbers, the Chinese remainder theorem gives us a ring isomorphism from ZQ, the integers modulo Q, to the Cartesian product of the sets of each of the integers modulo Qi. So you can apply this to optimize operations on large operands. First, you break each operand down into tuples, where each element in the tuple can fit into a computer word. Then you can carry out operations component-wise on the tuples, using the fact that the Chinese remainder theorem defines a ring isomorphism. And then finally, you can reconstruct the large result or results from the operated upon tuples. Unfortunately, not all of the BFE scheme can be trivially modified to take advantage of RNS. In particular, rounded division and centered modular reduction cannot be done in RNS. To overcome this challenge, full RNS variants of the BFE scheme, as well as other crypto systems, have been devised. In these full RNS variants of various crypto systems, conversion from the RNS base Q to a base B is often required. A fast base conversion is defined by the formula shown here. Note that we have some interesting forms of numbers here, in particular the Qi over Q and the number Xi times Qi over Q mod Qi. When the numbers Qi are chosen in a special form, these formulas can be optimized, which is the core of a lot of our work. The formula for decryption in the RNS variant of BFE is as shown here, and you'll note that it requires multiple base conversions. Similarly, homomorphic multiplication in the full RNS variant of BFE, as shown here, requires multiple base conversion operations, and some operations that use formulas similar to the ones we saw in base conversion. Previous work in using CRAM for BFE showed an improvement against highly optimized CPU libraries and a state-of-the-art FPGA implementation, even without using the algorithmic optimizations of RNS or NTT. The obvious next step in this work is to further improve BFE and CRAM. We can do this by exploiting CRAM's natural advantages in parallelism and flexible word size. Because CRAM's best performance comes with a constrained set of parameters, we find additional optimizations with that constrained set. We aim to choose RNS moduli that are close to powers of 2, so that modular reductions can be optimized. For a balanced set of moduli, we consider the first balanced set S1 to be 2 to the g for some number g, and the numbers on either side. These moduli admit certain optimizations useful in base conversion. The first lemma shows that these numbers Qi over Q have special forms that can make multiplication by them easier. And in some cases, as shown by this theorem and the ones on the next slide, we can even make this multiplication faster by not having to do any multiplication at all, but being able to do the multiplication and modular reduction in a single series of fast bit operations, as shown by this theorem, and by the lemma and theorem on this page, which also show fast operations for multiplication and modular reduction for the other two moduli in the set. Next, we'll also consider an unbalanced space. Elements of the form of the set S2 will form a set of coprime moduli. This set's inverses are powers of 2, which allows the multiplications in fast base conversion to become bit shifts. Further, these moduli are 1 away from a power of 2. So we can combine these and implement a multiplication of a number by those terms as circular bit shifts, which is much more efficient than a full modular multiplication. For the number theoretic transform, we require that 2 nth primitive roots can be easily found. Our moduli choices enable this, as shown for moduli that are at a power of 2 or offset by 1. We choose moduli in extended bases more traditionally, so this doesn't allow special modular reduction or base conversion, but Barrett reduction is still available for efficient modular reduction. Now we'll talk about our experimental evaluations. So in our experiments, we used a 16 megabyte CRAM size, which is built of approximately 16,000 arrays of 8 times 1024 size. Simulation is done in software with cadence and synopsis because actual fabrication of CRAM of this size would need years and millions of dollars to create. So, as the table shows, our CRAM parameter sizes match or exceed comparable work in FPGA implementations of BFV and CKKS schemes. We see improvements of 2 orders of magnitude from applying the number theoretic transform, and greater improvements from the cases using our special new optimizations. In this evaluation, we consider 2 data transfer rates, the specified and empirically measured transfer rates. Next, we'll talk about the comparison to CPU. So in our CPU experiments, we compared against the Microsoft Seal library, which was running on any of these 3 computing environments shown here, which are chosen to represent ordinary server, research workstation, and laptop environments. All of these computers were running some form of Linux. In our CPU comparison, for the important operation of homomorphic multiplication, we see improvements of over 700 times in runtime against CPU servers. For overall performance, this table shows the number of operations per second that our CRAM system was able to achieve. For homomorphic multiplication, we can achieve over 3,000 operations per second. This slide shows our work as compared to related work. The first table shows our CRAM implementation speedup of homomorphic multiplication against a high-performance FPGA implementation. The second table shows the speedup of CRAM against a GPU implementation of BFE. In both cases, we see a speedup of at least 1 order of magnitude for homomorphic multiplication. We roughly estimate over 8,000 homomorphic multiplications per second for CKKS using CRAM. This is comparable with the over 2,000 per second that was shown by HEAX, a high-performance FPGA implementation of the CKKS scheme. To conclude, in this work we applied algorithmic optimizations to further accelerate the BFV, somewhat homomorphic encryption scheme in CRAM. For homomorphic multiplication of the BFV scheme, our approach achieves speedups of over 700 times against a CPU server, 500 times against previous work in CRAM, 60 times against an FPGA acceleration, and 30 times against a GPU implementation. Some future work in this area lies in implementing more schemes such as CKKS, more work in improving the overhead from data transfer, and developing and using more CRAM capabilities, for example, floating point numbers. Thank you for listening to this talk. The final 2 slides are just references.